In this video, we will be talking about what dark matter is, proof of its existence, and the current research on the topic. To introduce the subject, dark matter is mass that cannot be detected by observing electromagnetic radiation, therefore it cannot be seen as it does not reflect, absorb, or emit light, hence its name. The existence of dark matter comes from observing gravitational effects it seems to have on visible matter, such as galactic rotation and gravitational lensing, which will be covered in this video. These effects cannot be explained by our current theory of gravity unless there is more mass that can't be observed. Since dark matter is hard to detect, there's currently no definitive answer as to what it exactly is. We can infer some basic characteristics of dark matter, such as it should not interact with observable baryonic matter unless through gravitational forces. There are three main candidates for dark matter: massive compact halo objects, weakly interacting massive particles, and axions. Our current understanding is that the universe is made up of around 5% baryonic matter, 27% dark matter, and 68% dark energy. This means that the matter that makes up galaxies and stars only accounts for 5% of the universe, which really puts into perspective the extremely large scale of it. The rotation curve, also called a velocity curve, of a disk-like galaxy is a plot of the orbital speeds of visible stars in that galaxy versus their radial distance from the center. Data from each side of the galaxy has been averaged out to create a curve. We can measure how fast stars rotate around galactic centers by looking at the frequency shift of known spectral lines originating in the stars due to the Doppler effect, for which the formula is shown here. As a star moves towards you, the wavelength of its light changes relative to the galactic center. Usually when we look at a star orbiting the Sun in the solar system, we recall Newton's law of gravity we've learned from high school, where we can calculate the centripetal force experienced by a star due to the Sun's gravity, and we find that the circular velocity is inversely proportional to the square root of the distance. The further away the star is, the slower it will go. However, when we observe a spinning galaxy, what we see is that the velocity of stars is completely independent from their distance to the center of the galaxy. As shown in the previous derivations, we expected a decline in the star's velocities when moving away from the galaxy's centers, but what we actually observed is that the velocity of these stars remained almost constant even when moving away from the center of the galaxy. Why does this happen? Why do stars go faster than we expect in galaxies? What is it? Is it faint stars, rocks, gas, or even dust? Why does Newton's law of gravitation disagree with our observation? The answer is, inevitably, the existence of dark matter, which in part explains the discrepancy between observed and predicted galactic rotation speed. Another proof of the existence of dark matter in the universe is a phenomenon called gravitational lensing, but to understand this effect, we first need to look at the bending of starlight near massive objects. Einstein's theory of general relativity outlines how mass concentrations bend light and space around them. This is due to the local curvature in space produced by the presence, in this case, of the Sun. Einstein's theory was confirmed at the beginning of the 20th century when he suggested observing the bending of starlight during a solar eclipse. English astronomer Sir Arthur Eddington led the expedition and found that light coming from bright stars 150 light-years away had been bent by the curved space of the Sun just 8 minutes before passing through his lens on Earth. Now, how does this relate to determining the existence of dark matter? Well, in a very similar way, we can ascertain the presence of dark matter based on the effect it has on the light coming from distant bright galaxies. Gravitational lensing occurs when light coming from these galaxies is distorted and redirected due to the gravitational field created by a huge amount of matter. Simply in the case of dark matter, unlike the Sun, we observe this effect through the presence of a mass that we can only imagine since it emits. On Earth, we observe gravitational lensing as a distortion, cropping, amplification, and even multiplication of images of bright distant galaxies. When the alignment between a distant galaxy and a galaxy cluster, for example, which distorts background light, is so precise, it can form an almost complete circle or horseshoe of light, called an Einstein ring. The magnifying effect of gravitational lensing can clearly be seen on this photo taken by the space satellite Hubble, with the presence of distorted galaxies seen as short lensed arcs on the outside of clusters. these galaxies have multiple images because of this effect. We can deduce the distribution of all matter in galaxy clusters, visible and dark, from the distribution of these lensed images, leading to maps of dark matter, here taking the shape of a ring formation, one of the strongest pieces of evidence of the existence of dark matter. Other evidence for the existence of dark matter includes the cosmic microwave background, which describes the radiation from the extremely hot time period at the beginning of the universe. Temperature fluctuations in the CMB can be used to determine the ratio of the 3 different types of matter in the universe. Although these proofs give us an idea on the effects of dark matter, they don't directly tell us what it is made up of, so this field will continue to grow as there is everything left to discover.